And it can be farther right, it can be farther left, it can be steeper, it can be less steep. The steeper curves means usually that this is a problem that requires some specific knowledge, and only if you are good enough to have the knowledge that you have a shot at solving the problem. So this is a very good model of what is going on in the competition. And this model is also interesting when you are doing the testing, because if you are testing some people and you give them tasks that are too difficult, you will learn nothing about them. Nobody will solve anything, you will see a rank with all zeros, you have learned nothing. If you give them tasks that are very easy for them, you will again learn nothing, because everybody will solve everything, modulo some random noise, again, no information for you. When testing, you gain the most information about the people. If the task you give them have this middle point somewhere around where their actual skill levels of the competitors are. And this is also true for learning. If you are trying to learn problem solving, you cannot learn on very easy tasks. Those are good just for practicing those patterns and consistency. You cannot learn on very hard tasks for you. If you don't solve any of them, you will not really learn. So the right point is somewhere in the middle. If you are solving tasks where you fail and succeed approximately at the same rate, this means that you are actually doing something good. If you are having failures but also successes, you have found the right difficulty for you, and this is where you learn most about the actual problem-solving process. Alright, and for the last part of my talk, I'm going now to talk about this problem-solving process in some more detail. So, clearly, you have been, all of you have heard questions like this one. How do I get from A to B in the shortest possible way? Or maybe, well, in the words of graph theory, imagine we have a graph with some vertices, some positive edges, and we are looking for the shortest path from A to B. What is the fastest way in which you can compute this? Okay, so probably many of you will come up with answers like, okay, Floyd-Warshall is very easy if it's small, and then Dijkstra's algorithm is even better, and we can implement Dijkstra's algorithm in something like OM times log n, or maybe even in Fibonacci heaps or something, whatever. So, Dijkstra's algorithm is a useful answer, but such kind of a knowledge that if I'm looking for shortest paths, I'm using Dijkstra's algorithm, this is in some sense superficial. You have the idea that this is an algorithm for shortest paths, but what we are actually looking for when we are learning to be a better problem solvers is some kind of a deeper understanding. So we don't stop here. We ask questions. For instance, we can ask the question, okay, but what if I actually give you a physical model of the graph, some balls, some pieces of string, what is the fastest way to find the shortest path from A to B? And now Dijkstra's algorithm is not the obviously correct answer. There are better ways, and actually you can do it in sort of constant time. If you want the best path from A to B, what you do is you grab the ball A with one hand, you grab the ball B with the other hand, and whenever it stops, whenever the strings become tight, you have just found the shortest path from A to B in constant time. The strings that are tight is the shortest path, and all of the others have some slack, and those are not. And you can actually improve this even better. You don't have to use two hands because you hold microphone in one hand, so you only have one hand left. And you can even find the shortest path from one vertex, vertex A, to all of the others. How do you do it? Instead of the second hand, you just let gravity help you. So you just grab it by the A, you shake it a little bit, and all of the balls will be hanging underneath the first one. So you will see a gadget that looks like the thing on the right. And again, all of the strings that are tight are the strings that are parts of some shortest path, and all of the other strings are useless. Now, what is the point of asking such questions? The point is that this actually brings you deeper understanding of Dijkstra's algorithm. Dijkstra's algorithm is just, we are constructing the very same gadget from the top to the bottom, and now we can, with this metaphor, with this visualization, we understand what's going on. We know we can easily prove its correctness, because the proof of correctness of Dijkstra's algorithm is essentially saying, if you have a ball at some weight, and then you add some strings below, it will not pull any ball above. So, if there is a line like this, and you are adding some strings here, those strings will never pull a ball somewhere here. And that's it. That's the entire correctness of Dijkstra's algorithm. And also, for instance, Imagine that you have a graph, you have already computed the shortest paths from A to everywhere else, and now you add a new edge. What does change in the graph? What is the part I need to recompute? If I visualize it like the balls, we add a new string, and you can see what happens. It lifts some balls higher. Okay, so let's get back to our original question. We are looking for the shortest path from A to B. But what if the graph is a map of Europe? Last time I played around with a map of Europe, it was a graph with something like 18 million vertices, 43 million edges, and now imagine you have your own server with some maps, and you want to provide directions, and you will have many people coming in and asking those questions. So again, is Dijkstra's algorithm the optimal solution? Not really. The green is showing you what the Dijkstra's algorithm has to traverse when you are looking for the connection from there to there. This is an actual map. There were some small algorithmic improvements, such as start the search from both directions at once, and this will only fill approximately like a quarter of the space only, or half. And during the years, since 1959, when Dijkstra first invented the algorithm, there were many improvements, such as the A-star search, using some heuristics to limit the space search. And only in 2005, so which is 10 years ago, came a significant algorithmic improvement called the landmarks. And the idea is you pick some landmarks along the map, you pre-compute the distances from everywhere to these landmarks, and then you can use some kind of triangle inequality to give you very good heuristics for the A-star search. So suddenly only those green and blue things that are shown on the map are actually visited by the algorithm that's searching for this shortest path. And then in 2006, and here, I'm sorry I have a mistake at the bottom, there should be one more maximum in the formula. There was a question what to do with things like this on the map. So what you can see is you are looking for a connection from A to B. There is a highway that connects them, and in the middle of the highway there is an island. And you have an exit from the highway and some edges there. And for a human, it is obvious that you cannot go, it doesn't make sense to go through the exit and then along those roads. But they are too far away from B, so the previous algorithms would still visit those vertices. Until in 2006, there was a publication of a paper with a new idea, a so-called reach. There is defined a mathematical formula how we can tell that this place is not worth visiting if you are traveling from far away to far away. And this has a nice mathematical definition, and it can be computed in polynomial time, and this is something that is actually done in practical applications. So at least, as far as I know, something like 4 years ago, many of the actual map servers looking for directions were still using these exact algorithms. Since then, we have again seen several additional improvements, because the research doesn't stop here, even though the problem is somehow solved, because the problem isn't actually solved. What we have today is, for instance, real-time traffic information. The real-time traffic information is real-time. It changes, and suddenly it means you cannot really pre-compute so much stuff, because many of the inputs of your program are changed. So we are still looking for better ways, better solutions to do this. And the entire future, from some point of view, is algorithmic, and these are pictures of some of the things my students are working on, starting from theory, when a few of my students published a paper on improving the lower bounds and upper bounds for actual number of swaps needed when sorting. The colorful picture on the bottom left is from an algorithm that does shuffling songs for Spotify in a better way, so that humans perceive it as more random. There are self-driving cars that are 3D modeling and printing and so on. There are many opportunities to change our lives for the better, and I'm very glad to be here with you, because it's you who are sitting here, who are competing in this competition, and who will be later on working on the future for all of us. And personally, I'm very excited to live in this future. I cannot wait what you guys come up with. So, thank you for your attention.
Thank you, Michal. Give me one sec. Apologies in advance. We had to use a few different programs, so there will be some switching in between, but bear with me. Our next speaker is someone who's a university dropout, who's never had a real job, and channeling your parents here, don't leave college. Although if you do, because it seems to be successful at times, don't mention you here at Bubble Cup. Somebody who actually makes a living by winning machine learning contests. Although apparently his professional career at poker playing helped, or at least it didn't ruin it. He has actually won many on-site competitions, such as Imagine Cup, 4 times winner of Top Coder Open, and Challenge 24, Deadline 24, and Marathon 24. Yet, amazingly, he doesn't actually enjoy programming. He also founded an indie studio where he works as a game designer and a game developer. Apparently, when he's introduced, they often call him either a hardworking guy or an outcast. I'll call him a hardworking outcast. His mom and dad call him Przemysław Daubiak, and to the rest of us in the world, he's known as Psycho.
Okay. I'll just try to grab it. Okay, let's see. That's not me. Yeah, so apparently I didn't know how Windows works, but it's Windows 10. Oh my god. Yeah. Okay, thanks. Just one moment. I need to set up my timer. Yeah. Okay. So my presentation will overlap a bit with Michal's presentation because we actually didn't cooperate with figuring out what we are going to talk about. So yeah, I'm going